Yeah, thanks, Hans, for the introduction, and thank you for inviting us to talk today. I guess my talk is a bit more on the technical side, and then Emma will be presenting, I guess, a broader overview of an application of geoscience in society. Yeah, I won't make any apologies though for the technical nature of this talk. I'll try and keep it broad, but at the same time, hopefully it shows quite a nice example of how technology is moving in the field of seismology, and how oil and gas companies are adapting their businesses or spin-outs from their businesses. So yes, I'll talk today about how we can use nodes to look at geothermal systems with an example specifically from Cornwall in the UK. So, So typically, when I imagine a geothermal system, I imagine we have a geothermal well, and when we're stimulating the system to try and produce energy from it, we pump fluids down the well in order to stimulate the rocks in the reservoir. And the aim, I guess, ultimately is to try and fracture those rocks to increase connectivity in order to make the geothermal system more efficient and produce heat at the surface. And typically, when we do this, we end up almost inevitably fracturing rocks. And obviously, we don't want to fracture these rocks and cause too big earthquakes. Otherwise, they cause induced seismicity that can be felt on the surface. And if there's any lessons to be learned from fracking, we really want to minimize that energy that can be felt at the surface. So typically, to do this, we monitor these systems using seismometers. And so here, these red triangles denote seismometers, and we typically deploy small networks of seismometers, maybe 5 to 10 seismometers at a geothermal site, because in geothermal systems we're typically limited. They're not as lucrative as say oil and gas prospects, so we just don't have the budgets to deploy large numbers of instruments. But that is slowly changing, or rather rapidly changing, I should say. So we can use fiber optic sensing, which I won't talk about in much detail today. But we can use fiber optic cables as many sensors that are far cheaper per channel cost than standard seismometers. And the other option we can use for monitoring these systems is nodes. And I think seismic nodes are particularly exciting technology because they're not limited by the single component nature of fiber optic cables. And they offer a similar per channel cost, maybe a little bit more expensive than fiber per channel. And so the reason we really want more receivers is because, firstly, we can reduce the noise levels, which lowers the detection threshold, which means we can detect smaller events and try and mitigate for the larger stress drops from larger earthquakes. And secondly, for higher resolution imaging, so we can use these earthquakes or active source methods to image where the fluids are in the crust, and therefore de-risk the drilling process. And the real driving change in this field is the availability of these seismic nodes. So typically, we used to deploy standard seismometers, which have a bandwidth from roughly 60 seconds to 100 hertz. And then we have these nodes. This is just a Stride node. So Stride is one company out of a number who are manufacturing these cheap, low-cost seismometer devices we call nodes. And they actually have a similar bandwidth to standard seismometers, at least in the range of frequencies which we're interested in. But the real difference is cost. So the cost per channel of a standard seismometer now is probably something of the order of $20,000. The cost of a node is something of the order of $100. Or technically, I guess you could multiply that number by 3 if you want a 3-component sensor, which is useful for some of the analysis I will show you later. But so these nodes are really revolutionizing the seismic acquisition purely based on the cost per channel. And so what we can do is, for example, at the geothermal site in Cornwall, we could deploy 450 of these nodes at a small fraction of the capital cost. Indeed, you can just rent these nodes as well, and so they become even cheaper to deploy. And they actually take less time to deploy than I think deploying 10 seismometers. It only took us 2 days to deploy these in the field and 1 day to retrieve. And that's just because they're so simple. They're all the components are in one sensor. And so what we did is we deployed these sensors at Eden geothermal site in Cornwall in the UK. And this is a 4-kilometer well with a deviation of 45 degrees from vertical. They inject fluids at the surface here, and we're stimulating the reservoir at depth, shown by the seismicity here. And we detected 250 earthquakes during a 25-day deployment. One of the things I really want to draw your attention to here is the receiver geometry. So in an ideal world, I would have deployed these sensors of an equal distribution, but unfortunately, due to landowner permissions, we couldn't deploy in this section right above the seismicity itself, and that affects the location estimates that I'll show you in the next few slides. But I think it really clearly indicates how we need to really get better at communicating with society what we're doing and the importance of geophysics in this work. The landowner was really upset that there was stimulation of earthquakes underneath his land, and that's why he didn't let us deploy in that area. But it's a real shame because actually, we could have understood and possibly tried to mitigate the risk of induced seismicity better if we could deploy on his land. Anyway, so what I'm going to show you is how we can use these nodes to firstly monitor seismicity, secondly try and measure at least qualitatively crustal stress state orientations. I won't talk in here about tomographic imaging, although I think it's actually another particularly exciting application of these nodal data sets. For example, for body wave velocity and attenuation studies, and also ambient noise analysis, as well as traditional active source imaging. So let's look at monitoring seismicity first. So what we can do is we can use these nodes as a network for microseismic detection. And so I typically use an algorithm that does a back migration of energy through space and time. And effectively, this is a really powerful technique if you have many sensors, because if you have an earthquake should have coherent energy coming from a specific location, and that coherent energy should be able to be back migrated from the receivers to the source. Whereas incoherent noise sources or noise sources outside the 3D grid search area shouldn't form coherent peaks in this space, and so we should be able to discriminate between, say, anthropogenic noise sources and microseismicity. And indeed, I think the two takeaways from this slide are really that we can detect an earthquake catalogue of 250 earthquakes, which is more than the standard seismometer network detected. And that owes to the fact that this method becomes even stronger the more instruments you add into it, or receivers you add in to the detection algorithm. And secondly, because it's encouraging that we can actually process this kind of volume of data. Here we have 450 sensors, and we can really easily run this algorithm in approximately real time. I just wanted to show you one of these events in a bit more detail. Here's a plot of time after the event origin time versus epicentral distance, so distance from the earthquake. And you can see the 450 receivers or so here, and you can see a really clear P wave arrival and an S wave arrival. And this is just the data with a simple bandpass filter applied. And I was really impressed by this data actually, considering these instruments $100 instruments made with piezoelectric sensors. They perform really well. We can then obviously look at spatial and temporal trends, which is one really important thing to do when we're looking at characterizing seismicity triggered by stimulation of geothermal wells or reservoirs. And we really struggled to see a clear temporal trend in time. But what we can see is I think we can just see some clear discrimination between two clusters of seismicity. One here, I don't know if you can see my mouse, but I'm looking at the far right-hand plot. A cluster roughly 3.7 kilometers below sea level, and a cluster roughly 4 kilometers below sea level. And these correspond to two inferred fault zones from the well logs, approximately. And so I think this gives us some confidence that we can at least approximately resolve the depth of these events. Obviously, it would be ideal if we had receivers over the seismicity itself. And I guess in a future deployment, we would really try and do a better job of communicating with the landowners in order to try and get the relevant permissions. But it just highlights one of the challenges involved with working in quite densely populated areas. We can also calculate magnitudes. I don't really want to take too much from this slide, other than we can calculate the size of these events using the nodes. This is a plot of cumulative number of events versus moment magnitude, and yeah, we can simply calculate moment magnitudes pretty robustly for this data set. And the only other takeaway from this slide, I guess, is that we see B values, so that's the gradient of this line, greater than 1. And that's really indicative that this seismicity is caused by fluids on faults, which is obviously to be expected because we are pumping fluids into a geothermal system with fractures, but it's a nice confirmation of that. And indeed, magnitudes are essential to calculate for any kind of monitoring strategy. If society is going to try and, well, if industry is going to try and mitigate for the risks of induced seismicity on society. So that's all I wanted to mention on monitoring seismicity. I just want to show for a few minutes what we can do measuring crustal stress state, which is obviously highly interrelated to seismic risk and hazard. So what I'm going to show you is I'm going to show you how we can measure crustal stress state at the injection site. I'm going to show you some earthquake source mechanisms, some fault slip directions, and some fault properties, just to give you a flavour of what we can look at and elucidate or shed light on in these systems. And then I'm also going to show you briefly seismic anisotropy measurements, which are a proxy for the stress state of the crust above the stimulation site. So firstly, a little bit on earthquake source mechanisms. Many of you may not have ever seen an earthquake source mechanism, so I thought I'd just briefly highlight to you what they are. So if you imagine an earthquake caused by two blocks sliding past one another, then you end up forming these radiation patterns with different quadrants. The black regions here are showing compressive first arrivals of P waves, and the white or pressure waves, and the white regions are showing tensional first arrivals of pressure waves. And we can use these radiation patterns to infer the orientation of a fault. But I just want to highlight that there's some ambiguity. So if we look at this fault from above, we typically represent these focal mechanisms as follows. And you can see that a vertical slip fault has the same slip direction apparently from these radiation patterns as a horizontal fault. And so that's worth bearing in mind as I show you these results. So what we can do is we can look at these earthquake source mechanisms. I'll briefly mention what I did to derive these technically, because that might be of interest to some people. So these are P-wave polarity constrained source mechanisms, constrained using automated polarity picks. When we use so many nodal sensors, it becomes very quickly impractical to manually pick these arrivals and the polarity of these arrivals. And so we actually found that the automated polarity picking worked really well for this quite high signal to noise ratio data. And you can see that exemplified by this focal mechanism here with quite a tightly constrained focal mechanism and pretty much no error in the polarity picks. And I think this also is a testament to how useful it is to have many nodes, as you can really quickly see if you have much uncertainty in your polarity picking algorithm. What we see is two sets of faults, roughly a few hundred meters apart, slipping in completely opposite directions. So if you look at these southerly faults, they have a complete 180-degree shift in the orientation of their focal mechanism. And you can even see that rotation as we move further north. And so what we think is going on here is we've got two sets of faults. We think these faults are failing vertically, and the central rock, I guess, in the center here is falling relative to the sides, likely caused by fluids interacting and reducing the normal stress on these faults. So that's quite interesting itself, and that's something that we couldn't see in the seismometer data, but we can see in this nodal source mechanism inversions. We can also look at S-wave source polarizations, and these can be used to look at the polarization of the S-wave, the shear wave, and that tells us about the orientation of the faults. Here we see a dominant orientation of the horizontal orientation of the fault, north-south, although we think this is just the horizontal component of a subvertical fault strike, but it fits nicely then with the moment tensor inversions. And this is only possible because we could deploy these nodes in a three-component orientation. And yeah, on that note, I was kind of a little bit skeptical that we could deploy these nodes, these single component measurements, sensors, in three-component orientations, but actually they worked really well. And this and the anisotropy measurements would not be possible without these three-component deployments. So we can now look at the anisotropy. So this is a measure of, this allows us to measure a proxy for the stress state above the injection region. So everything I've showed you so far is at the injection site. And what we see at the injection site, just to remind you, is we see fractures oriented roughly east-west. But above that, the anisotropy suggests we actually have fractures oriented at sort of 30 degrees from north. And this could be caused by fractures, or sorry, it could be caused alternatively by crystal preferred orientation. And I'll show you some well-logged data in a minute that backs up this observation. But this is a really interesting result because this suggests that the crustal stress state at the injection region is different from the crustal stress state above the injection region. And that has significant implications because typically when we assess the stress state of these geothermal systems before we drill or inject fluids, we'll often use geological measurements or say world stress map data that is looking at that top crustal stress state rather than the stress state at the potential injection site. And this is just saying that again, that when we look at the world stress map data, you can that paints a different picture again, and we think we have sigma H max in this orientation, roughly 130 degrees from north, which doesn't fit with the fractures we observe at the stimulation site. Just to finish on that with that story and back that up with some auxiliary data. If this blue line is the borehole, then at depths at the injection depths, we see dominant fracture sets from ABI imaging with fracture strikes roughly 130 degrees from north, and that matches really nicely with sort of our results from the moment tensor inversions, the source mechanism inversions, and to some extent the S-wave source polarizations. And then as we move up and look at our anisotropy results, we see fast directions that strike roughly 20 to 30 degrees from north, 30 degrees from north, and that fits really nicely with what we see as the dominant fracture sets from the well logs from FMI imaging. So it really gives us some confidence that we have this switch in stress state at the injection site versus in the overlying crust. And I guess this just summarizes in a different way, but I will skip over that because I think I've already described this slide. A final observation I just want to show you, just for interest, is that we can also use these nodes to characterize the radius of the faults that are failing. And interestingly, for any seismologists out there, we can calculate the stress drop of these earthquakes versus the seismic moment. So the size of the earthquake versus the amount of stress released during each earthquake failure. And because we have so many sensors, we can really constrain the uncertainty on these observations really well. And you can see a clear linear trend between the stress drop and the seismic moment. And for those of you who aren't earthquake seismologists, this is a real area of contention in seismology is do we see any variation in stress drop with earthquake size? And I think this data set really clearly shows we might. but that kind of contradicts some global seismic data set observations. So if we put all this together, as I finish up, we can look at monitoring earthquakes using these nodal arrays, and we can detect more events using these new sensors. And we can also calculate fault properties, including the moment release, fault orientations, fault radii, stress drops, and the orientation of the stress state, both at the injection site and above in the crust above. And much of this wouldn't be possible or is significantly enhanced by this step change in sampling density of the seismic wave field that is provided by these new nodal technologies. And indeed, I think these nodes, in combination with, say, fiber optic sensing, are really going to revolutionize how we can image these geothermal systems at a cost that isn't prohibitive to industry. Yeah, thank you for listening, and yeah, feel free to ask me any questions.
Brilliant. Okay, thank you very much. Yes, as Tom mentioned as well, I will apologise for my presentation not being quite so technical. It's what I want to talk about is, for the next 20 minutes or so, is a project that I was involved in a year or so ago. It was looking at how geoscience as a discipline can advance the United Nations Sustainable Development Goals. So I will present this on to you. Just let me know that everything's okay, that you can see everything okay. But just, yeah, I suppose the reason that we did this was really just looking at the value proposition of geoscience and how the narrative does start well. I have young children myself who are very interested in dinosaurs and volcanoes and even gemstones. And as they get older, kind of move away from seeing geoscience, I think, as being a subject that they'd potentially be interested in. I think generally there can be a perception around climate and biodiversity crisis, and the fact that geoscience may play a negative role in that narrative. So I think generally there's a poorly understood aspect, I think, of geoscience regarding its contribution to kind of economy, environment, and society. This isn't really anecdotal. There are a lot of, we had this conversation at the very beginning of the talk with Hannes as well about the uptake, the reduction in the uptake of geoscience as subjects. For example, in the UK, students are declining year on year since 2014. This is kind of more of a global trend as well. Not being just in the UK and in Europe, but actually broader than that. So also geology departments closing down as well, Australia, all over the place really. And yeah, there's this perception, and there was a paper, I just received it a few weeks ago from Geological Society, it's from Earth Science Systems and Society publication, where they actually did kind of a fairly detailed quantitative analysis and surveyed people around the reputation of geoscience, and a combination, I suppose, of geoscientists and non-geoscientists. Remarks such as being old-fashioned, boring, and environmentally damaging, as well as things like they just look at rocks and they have beards, were some of the things that came out. Also, and I know that we mentioned this as well at the beginning of the talk, the poor job prospects outside, and I would nearly say as well inside of the extractive industry is another reason potentially for people turning away. So there is a need to reboot the subject and ensure we have the skills needed in the future for the pipeline of the subject itself. And there are lots of different initiatives afoot to do so. And I suppose what I'm going to talk about is one of them. But I suppose before we go into that, a little bit of kind of, looking at ourselves as a discipline and the unique proposition, I suppose, that comes from geoscientists. We are unique as we possess a holistic understanding of the processes that shape our planet. In the fourth dimension of time as well, we have a good understanding of rise and fall of mountain ranges, opening and closing of oceans, and formation and location of a broad spectrum of energy sources. We have a good understanding of how these processes are interrelated, how we can extract resources in the most sustainable way possible for the future, for a sustainable future, and also how we can mitigate and adapt to the impacts of climate and environmental change. So this is something that we as a discipline understand. It's not something that's broadly understood though. So I think that was kind of what we wanted to try and change to some extent, to a small extent, the narrative of that. So the United Nations Sustainable Development Goals are the world's shared framework on sustainability. They're a really widely recognised blueprint to move the planet and its people towards a sustainable future. So it very much made sense for us to align and to map the subject of discipline of geoscience to the Sustainable Development Goals to shine a spotlight, I suppose, on our contributions. So what we did was and I say we being about 12 authors from pretty much every continent, representing quite a broad cross-section of disciplines. So we had volcanologists, oceanographers, energy professionals, disaster risk reduction experts as well, those in sustainability, those coming from NGOs, academia, industry, communications world as well, as you can see in Stuart there. What we wanted to do for this and this mapping process and this publication was really to raise the awareness of the role of geoscience and geoscientists among geoscientists themselves, not just outside, and also for society at large. We want to elevate the understanding of how geoscience advances each of the 17 SDGs, share the enthusiasm about geoscience career prospects for the future, being cognizant of the concerns that we have for the pipeline, both in industry and academia, etc. And establish a platform of communication about the value of geoscience and a framework for future contribution to sustainability. So we mapped geoscience to all 17 of the SDGs, looking at things like energy, things like disaster risk reduction, the provision of all low carbon energy sources, water, as well as on land, sustainable cities of the future, etc., agricultural geoscience, construction, etc. This is something that we did previously, a couple of years previous on geophysics, but we broadened it for this particular publication out to a broader geoscience remit. For this, we actually wanted to not look at each of the SDGs, each of the 17 SDGs in silo, but what we wanted to do was to look at the 3 Ps, and this is the 3 Ps, which is what the United Nations would use as well, of people, planet, and prosperity. So people being positive impact on individuals, planet being the positive impact on physical systems, and prosperity, the positive impact on social systems. We thought by doing that and by bringing those together, we highlight how the SDGs are very much intertwined. There's a huge interrelationship between each of them. And I think by looking at them as the 3 Ps, it meant that we were measuring progress a lot better. So the process, I won't go into any much detail, but it took a while. What we wanted to do was identify the geoscience disciplines, methods, and the tools that were relevant to not just the 17 SDGs, but the 169 targets and 231 unique indicators of the SDGs. So we wanted to feed into that and then classify the SDGs towards which the various dimensions of people, planet, and prosperity. And then establish, I suppose, the dominant SDGs per dimension for each of the geosciences. So yeah, I suppose what we want to do is show how interconnected the framework is. We say people, planet, and prosperity. We can kind of equate or interchange those phrases for people being the social, planet being environmental, and prosperity around economic change, because obviously there's a broad understanding that sustainability requires all 3 of these dimensions. So all of these were looked at all together. In addition to that, there are 2 goals that the two SDGs that appear everywhere, those being SDG 16, which is for peace, and SDG 17 for partnerships. So we felt that they were integral part of all three of these dimensions. So what we did was we did a call for, we wanted this to not be just a desktop study, but actually to be something that involved the geoscience community at large. So we called for requests for kind of examples demonstrating how geoscientists are contributing to achieving the goals. So we did a public call, we did a call on social media for people to provide their examples, and we had a good cross section. The map that you see there really just represents planet in terms of dimensions, so you can triple that in terms of the examples that we received. It was great to see the amount of examples that were submitted. Unfortunately, we were only able to use some of those examples, but this is work in progress, and there's a lot of activity taking place, since its publication. So just a quick example, I suppose, of some of the examples that we received. We received, for example, for SDG 1, we had an example on reducing the vulnerability of communities to natural disasters. So we had the Global Earthquake Hazard and Risk Model example. With each of these examples as well, we went into some degree of detail on the technical skills required for the execution, I suppose, of each of these projects. So seismology, GIS, seismic hazard modelling, etc. We also had an example from India around the sustainable extraction of water supplies from floodplains to supply the population. And again, you looked at all the kind of the techniques, the geological techniques and geophysical techniques needed for that. For SDG 16 around peace and prosperity was a really interesting example I'd heard of before through the SEG, which was mapping mass graves and escape tunnels. So using geophysical mapping, magnetometry and drone-based mapping to map mass graves and escape tunnels from the Holocaust victims in Poland and Lithuania. So really, we really wanted to show the broad application of one particular discipline, geoscience, and how tools can be repurposed and reused across for various different objectives. This is just a few examples for planet. We had things like multi-scale assessment of forest ecosystems. That was in Asia. We had benthic habitat mapping, understanding protecting the fish spawning grounds as well. And also something, I suppose, of more familiarity potentially with this group, and just showing that within the oil and gas industry plays a huge part in the acceleration, positive acceleration of these SDGs towards the 2030 agenda. So this was an example of the Northern Lights carbon capture and storage project. And then I suppose some of the other ones around, we call these under prosperity. It was quite difficult to classify which was people, planet and prosperity. So they're certainly open to argument. We had the kind of the communication side of things. So the creating geoscience awareness in Namibia. So they had a nationwide outreach geoscience awareness initiative where they had broadcasting programs as well around geoscience. We have also a huge issue, and this is highlighted as well in that publication by the GSL around gender inequality in geoscience. So there were some examples there of various initiatives that were trying to tackle this. It's a huge issue, I suppose, as well in terms of intake of geoscientists as well. But what I'm seeing in academia as well is the kind of the progression, the career progression as well, and the disparity there for gender. We also looked as well at affordable and clean energy. So this was geothermal energy from the East African Rift. So this is more of a community geothermal project as well. So that's just a few of the examples that we did receive that form part of the publication. And again, long lists of the skills required for each of those as well for people looking to see where their skills kind of can be mapped out as well. But a big part of it as well, and I suppose in addition to this repurposing of skills to support the SDGs. So I suppose a real obvious example is oil and gas skills, and as Tom had kind of shown there as well, to explore for geothermal potential. or delineation characterized storage sites. This kind of repurposing cross-disciplinary skills were things that we highlighted as well, that were required as we move towards more sustainable solutions. And as we do that, I think Tom highlighted it as well in terms of densely populated locations as well. There is a skills gap, I think, that needs to be filled as well. And this is something we concurred, and it's been mentioned a lot recently, is the increasing need to interface with society for the green transition. So it can be both arduous and contentious in terms of trying to get projects over the line. Whether that be critical raw materials and the need for those in order to supply the technologies such as wind turbines and EVs, etc. That kind of conversation, that communication, that understanding is hugely important, and that's a skill set, I think, in itself. Obtaining licenses as well for things less contentious, or so you would imagine, around offshore wind turbines, or also restoration projects for peatlands. Things like that can be contentious as well, and they're all around just transition, and require that societal interfacing and that kind of societal skill set, I suppose, and competencies. So another thing that we did as well was we looked at the kind of stakeholder analyses and the importance of stakeholder analysis for the discipline as well, in terms of preservation of the discipline. We do use the term informally to define significant groups involved in sustainability and what their relationships are to geoscience. So we look at essential stakeholders, those of high influence as well. We look at immediate stakeholders, less influence there, interest in geoscience and its application. And also we look at adjacent stakeholders and peripheral, and kind of just divided up the public, because people talk about the public all the time, and the public actually is a lot more broken down and siloed than just one particular public. So yeah, geoscientists really need to work both with engineers, planners, to build sustainable cities of the future. So we have to be part of the jigsaw puzzle, I think, is one thing that we were concluding as well. It's we think we're great, and we play a huge part for sustainability in the future, but that is very much, part of a broader group of scientists, and also environmental scientists, social scientists, etc. So we have to really extend our interactions into the social sciences to engage and communicate our value proposition, and I suppose the place that we're going to play, and the part we're going to play in sustainable society of the future. And some examples, I suppose, are around getting geothermal projects over the line with policymakers, business leaders, legislators, making sure that that we're communicating what's needed and and what we require to enable it. So defining and mapping stakeholders in geoscience can help us frame the opportunities to develop strategies for outreach, to work on solutions that geoscience may bring activities towards the sustainable goals. And I suppose a few examples of this stuff that I'm seeing. So I work, as Hannah's mentioned, in academia. We have about 150 geoscience researchers, and not just geoscientists, but we also have botanists and environmental scientists. But in addition to that, we have a lot of social scientists and psychologists. And we're finding, and this is academia, but I think it's going to be the case in industry as well, that, for example, reaching our net zero energy targets, for example, offshore wind. For offshore wind, it's not just from a geoscience point of view, the geotechnical constraints of where you put your turbines, but also the biological, the environmental, and the social constraints that are that play a part there. So actually combining all three and looking at it holistically is hugely important. And I think that's similar to what Tom was mentioning on the geothermal side too. As well as that, there are things like the importance of critical metals for the energy transition. Working on the narrative of mining, again, in publications, in surveys that are done with the public. There's a lot of talk of mining being dirty and things like that, but actually trying to change the narrative towards the importance of exploration of critical metals in order to supply the green energy transition. It's hugely important. So we work a lot in our research centre on things like that nexus of society with the resources and the importance of opening up those conversations as well. So yeah, I suppose a concluding remark and something that we all concluded, and I think it was quite fitting that we all, as authors, came from different places, both geographically but also from a sectoral point of view, and came together in an alignment with SDG 17, but just on a broader view, the global goals, and this is what's said all the time, can only be met if we work together. So a huge kind of learning and takeaway from this process as well was recognising multi-stakeholder partnerships being a huge part in terms of mobilising the SDGs going forward. Storytelling, communication, outreach, and I suppose marketing what our subject is and what we bring to a much broader group of audiences than maybe what we're used to at the moment. So that's just a few reflections, I suppose, on the Atlas. The reason we did it was to showcase how geoscience is the importance of geoscience for the 2030 agenda, that we have a huge part to play. We wanted to show the diversity as well of contributions coming from geoscientists that can also be resonate, I suppose, and inspire the next generation of geoscientists as well. We wanted to foster collaboration within the community, and not just within the community, but outside the community as well, and just offer a framework and a platform for communication going forward for this. So that's all I have to say. So thank you very much for listening. I'm happy to take your questions too. Thank you.